Hi guys, welcome to this video. I'm going to be discussing how to design a slender column based on a BS standard. A column is referred to as a structural component that is majorly subjected to compression load and sometimes can also resist bending moment. We have different forms of column based on the construction material or based on the type of load they resist and also based on the geometry. The classification of column is either short or slender is governed by the geometry of the column, and we use the term slenderness ratios to determine if a column is short or if a column is slender. A short column tends to fail by shear or through compression failure, which can result into crushing, while a slender column, as a result of the length of the column compared to the size, it tends to deflect a little bit. So this deflection results to buckling failure. So the first image on the left hand side is representing a short column failure, while the second image is representing a failure from a slender column. You see it deflects a little bit and then makes the column to buckles. In order to design a slender column, we must first establish that the column is slender. In order for us to do this, we need to understand what we call the slenderness ratio. And the slenderness ratio differs based on different type of columns, based on the load they resist. Based on the load columns resist, we have braced and unbraced. A braced column is the one that resists mainly gravity load and does not support lateral loads. Lateral loads such as wind load, earthquake loads. While an unbraced column is the one that is designed to support gravity load as well as lateral loads. In form of braced column, it is important for us to provide alternatives that take care of the lateral loads, such as the shear wall, the staircase well. So those structures are important if you don't want to use your column as a resistance for lateral load. So in case of a braced column, the column is considered to be slender when the slenderness ratio in both directions is greater than 15. X and Y represent the major and minor direction. L in this equation, LE, represents the effective length of the column, while H and B represent the size of the columns. B means the shorter side, while H means the longer side. So let's say a column is 300 by 450. B in that case is 300, H in that case is 450. In case of an unbraced column, for the column to be considered slender, it has to be greater than the slenderness ratio, which is the ratio of the effective length to the size of the column, must be greater than 10. So we know how to determine B and H. So how do we determine the effective length LEX and LEY? This diagram is going to give you a brief understanding of how LEX is determined. This actually depends mainly on the end condition of the column. So the end condition of the column determines the size of the LEX, the effective length. So consider a column of 5 meters. When the end of the column, both the top and bottom part of the column, is a pin condition, then the effective length is taken as the clear length of the column. Then when the column is considered as a free end, that is probably the column is a cantilever, has a fixed support, then you can take that kind of column, the effective length of that column as twice the clear length. So example of this is a gate column. Another situation is when you have the base part of your column to be fixed, and then the top part of the column or any part of it is pin or a roller support. So that kind of situation is a pin support. The effective length of the column is taken as 0.7 multiplied by the length, that is 7%. So it actually depends on the end condition that determines the value of this LEX. The most common situation is either you have condition C or condition D. So most of the time, especially in reinforced concrete buildings, the column are designed to be fixed at both the top and the bottom end. So in that case, you can take your L naught to be L over 2, or when you make the base to be fixed, and then at the slab region, in case of a flat slab, you make it a pinned condition, so your L naught can be taken as 0.7 L. So what are the procedures that you need in order for you to be able to design a slender column? I've already created a video giving a detailed explanation on how to design a short column. You can find the video in the description of this video. In order for you to be able to design a slender column, the first step is to analyze the column to determine the axial load on the column, and if the column is subjected to bending moment, then you also determine the bending moment. So from that, but due to the internal stresses in the column and also that the column is slender, there's going to be an additional moment due to that. So you have to calculate that M add. In order to calculate that, you need to assume a value of K to be equals to 1 and create your first iteration. So with your first iteration, you are going to get a new value of K. So you have to keep repeating this sequence until you can arrive at a constant value of K. When you arrive at the constant value of K, you use that to calculate the required area of reinforcement, and then you provide the reinforcement. This might look a little bit confusing, but when we take a work example, you are going to understand it clearly. So we have some little formulas for this. The formula for MT is MI. This MI represents the initial moment on the column from the analysis. The initial moment that was subjected to the column based on the loadings. That's MI. M add is the additional moment due to the geometry of the column. Because the column is slender, then the column is subjected to an additional moment. So the next thing is to now calculate M add. To calculate M add, we have this formula NH over 2000 KLE square over B square. N is the axial load, which was calculated from step 1. H is the longer side of the column. Let's say the column is 300 by 450. H in that case is going to be 450. K in this case is what we use to calculate to create our first iteration. The value of this K must always be less than or equals to 1. So that is why for the first iteration we are assuming K equals to 1. And then the LE is the effective length of your column that is determined based on the end condition of the column. Then the B is the smaller side of the column. Like I've mentioned, if your column is 300 by 450, B in that case is going to be 300. So once you determine your M add, you now add it to the initial moment to get your OM total. Then with this, you can now calculate the value of required area of reinforcement. So let's now take an example. But before we do that, I'm going to introduce you to one of my courses in learning manual design of reinforced concrete to the BS code. You can take this course. It's a project-based course, and you are going to learn how to design a building from start to the finish end manually. So you learn how to design building from start to end. Then you also get access to calculation template for all structural members like beam, column, and slab, as well as the foundation. You learn the full rudiment of the basics of design, and you also learn how to create general arrangement from architectural design. So this course is a project based, and this one is for design to the BS code. If you are conversant with the Euro code, so manual design to the Euro code, you can also take this one. This course is actually divided into parts. We have introduction part, the structural loading and analysis part, the structural design part, and also the detailing part of it. So you can see what you are going to learn. It covers the design of ROC members using the Euro code manually, A to Z. And also you learn a brief introduction of how the Euro code come about and how you can compare the Euro code to the British standard. You also learn a lot of things on design of structural components like slab, beam, column, staircase, foundation, as well as detailing. So I'm going to leave the link to these two courses in the description of this video. You can take them to get more in-depth knowledge on what I'm explaining in this video and also the design of other structural components. So let's take a work example on design of slender column. So we are going to use a column of size 230 by 300. This is just an example. And then from the analysis, the axial load on the column is 900 kilonewton. We determine that the bending moment of the column is 50. And then the FCU, the characteristic strength of concrete, is 30. The FY, the characteristic strength of steel, is 460. So you can say that this column is uniaxially loaded because it has movement in only the major direction. So assuming that we have bending moment in X and Y, that means the column is biaxial. So this example is design of slender column in uniaxial case. So based on this parameter, we can say the B is 230, H is 300, and then let's assume our effective length of column to be 6 meters. Then we can now calculate our slenderness ratio based on the shorter side, LE over B, 26.1, LE over H. If you divide this by this, you get 20. So then from this, to now calculate our M add, because this is a slender column, we've already established that this is a slender column because 20.1 is greater than 15 if the column is braced or even if the column is unbraced. So from this, we can now calculate our M add because the column is slender. So M add is given by this formula, NH over 2000 KLE square B square. So substituting N, which is axial load, H, which is 300, K, which is 1, we are assuming 1 for the first iteration, and then LE, which is 6 meters, B, which is 230, into this formula, we are going to get M add to be 91.87. That is the moment due to the slenderness of the column, regardless of the external moment added to the column, is 91.87 kilonewton meters. So since we calculate our M add, the next thing is to calculate the M total. M total is just addition of the initial bending moment on the column based on the analysis, 50 plus 91.87. So we are going to arrive at this. So once we get this, how do we design column normally? To design the column, you need to establish D over H, especially if you are using the British standard. D over H in this case is 0.8. So we are taking our D to be cover, D equals H minus cover minus links minus half diameter of bar. So if you take a cover of 40 for your column, a shear length of 10 mm and a bar size of 16 mm, so you are going to end up with 242. If your H is 300, we are using H of 300. So in that case, D over H is 0.8. Then we can now calculate N over BH. N is the axial load, 900 divided by width, the two sides of the column. In this case, we arrive at 13. Then we now have to do M over BH square, because in design of column, most of the time we make use of the design chart. So we need to establish these three parameters before we be able to use the design chart. So M over BH square equals 6.87. And this M is the M total that we calculate, not the M add or the initial bending moment. The M in this case is going to be the M total. So the next thing we have to do based on the step, we finished step 1, the analysis. Step 2 is to determine M add and MT, which we've done. The next thing is now to determine a new K. How do we determine a new value of K? We can do that using the design chart. So we are going to be using the normal column design chart that we all know. And in order to select a chart, you need to use these three factors: the FCU of the concrete, the FY of your steel, and D over H. So our FCU is 30, FY is 460, D over H is 0.8. So that's why we select chart 27. So along the x-axis is N over BH, along the y-axis is M over BH square. So you just need to read 13, which is N over BH. This is 13. The purple line is on 13. And then the second one is 6.85. So 6.85 is around here. It's going to be around here. So this 6.8, 6.85 is going to be around here. So at the end of the day, you can see that the intersection is intersecting around this location. So you can see on this graph or on this chart, we have different curves. We have curve 0.4 to curve 8. So this is curve 0.4, followed by it is curve 1, next is curve 2 up to curve 8. But what we want to do here is, we are not providing for the area of reinforcement yet. We want to have a steady value of K, and K is represented on this graph or on this chart using this dashed line. You can see this dashed line here is say K equals 0.1. The second dashed line say K equals 0.2. The third dashed line 0.3 up to K equals 1. You know, I told you the maximum value of K is 1. So it ranges, it must always be less than 1. So now, based on our readings, the x-axis, reading the x-axis against the y-axis, it intersected here. So if you look at the readings, you can see that it falls between K equals 0.7 line and K equals 0.8 line. So this is K. All these dashed lines are K. So in that case, we can assume, based on approximation, that our K equals 0.77. Based on this, you can see 0.8, very close to 0.8, more than 0.7. So you can say K equals 0.77. So because of that, we assume a K equals 0.77. The next thing we have to do is, based on this value of K, you determine M add. Now I told you, you do this until you have a steady value of K. So you substitute this, our new K, into the formula of M add, which is NH over 2000 K LE square over B square. The other parameter remain the same. The only difference is K. So that means earlier we have a K of 91 point something. So you just multiply it by 0.77, since we use a K value of 1. So that's why you arrive at 7 point something. That's how we get this. So since we get a new M add, you now have to determine a new MT. MT is just initial moment, which is 50, plus our new M add. So doing that, you arrive at 120.74 kilonewton meters. And then from this, you know, our value of D and H is the same. N over H is the same. MB square is also the same. So if you do this, you get a value of so with these three parameter again, you go to the chart, you read 13 against 5.82. You can see that what is changing is the moment. That is changing. 5.82, with 5.82, we are going to be having something around here. So that means your K is going to be around 0.72, something like that. So we are going to get another value of K. Doing that, you get another value of K of 0.72. So if you do this, you get a new value of M add by substituting into the value of K. Then you get another new MT. Then you do the calculation again to get M over BH, M over BA square, and then you come to the graph and read again. So if you continue doing this, at the third iteration, you are going to see that after the second iteration, your K value is going to be rounding up to 0.72, 0.71 or 0.72. So because of that, we are going to stop at the second iteration, because our K value becomes steady at the second iteration, where we get a K value of 0.72. You can try to read the graph of 5.61 against 13. If you read 5.61 against 13, you are going to have something close to 0.72. So because of that, we just use a K value of 0.72. So once you determine K value of 0.72, which is this one, you can now calculate the area of reinforcement. To calculate the area of reinforcement is very easy. Just like what we've explained in our previous video on column design for short column, you look at where the intersection falls, the intersection falls here, and look at the percentage of reinforcement that is close by. So we can see that the intersection of X and Y is close to the core 4 and core 5. But you have to be very careful. If you are designing based on the BS standard, the maximum percentage of reinforcement is 6%. But in this case, you are getting something close to 4.6 or 4.7. So let's go with 4.6. So you equate whatever you get in the chart to 100 AS over BH. AS is the area of reinforcement that we are trying to determine. So making ASC the surrogate of formula and substituting the value of B and H, we are going to arrive at ASC, that is the area of reinforcement required for the column, is 3174 millimeter square. So in that case, we are going to provide a reinforcement of 8 number of 25 diameter reinforcement, which give us an area of 3926. So based on this, we can now say that our column, when designed to be slender, requires 8 number of reinforcements. So that means you have to have 4 reinforcements at the bottom or at one face, and then 4 reinforcements at the other face. While this side is 230, this is the detailing of the column, and then this side is 450. So sorry, it's 300. So you can see that detailing wise, this column is not adequate, because the maximum area of reinforcement required by this section is more than, you cannot provide 4 number of 25 mm reinforcement on a 230 face of column. So in that case, in the design part, it is advisable for us to increase the size of the column, either going with a 450 by 450 column or 300 by 300 column based on this design. But with this video, I'm sure you can now design a column, a slender column. The first thing you have to do, to recap on this, is to analyze the column. Once you analyze the column, you determine the moment and the axial load. Then you now determine if the column is a slender column. If it satisfies the slenderness rule, then you have to calculate the M-add, the additional moment due to the slenderness of the column, which is calculated based on the formula that I gave to you. In that formula, the only unknown is the K. So we are going to assume a value of K equals to 1. With that value, you calculate M-add. You add your M-add that you got to the initial moment to calculate the total moment. With that value, you now come to your column chart. You read N over BH against M over BA square, and then you determine a new value of K. With your new value of K, you do the same thing again. You calculate M-add and M-total, and then come to the chart. You do this until you get a steady value of K. So once you get a steady value of K, whatever the intersection of N over BA square is at that point is going to be your percentage of reinforcement. And with that, you can provide for the reinforcement. If you enjoy what I've shown you, but you also want to learn how to detail reinforced concrete column, you can check this video right now.